Now we can evaluate the mean square value of output random process y of t. So we already know that this ryy of tau is equivalent to integral minus infinity to plus infinity h of tau 1, and here we have minus infinity to plus infinity h of the rxx of tau minus tau 2 plus tau 1, is it? And this is integration with respect to tau 2 and then with respect to tau 1, is it? So this is the autocorrelation function of the output random process y of t. So we already know that the mean square value of the process can be obtained by simply letting tau equivalent to 0, that is ryy of 0, so which is equivalent to the minus infinity to plus infinity is h of tau 1, here this is h of tau 2, this is rxx of tau 1 minus tau 2, so d tau 2. So what this indicates, if you know the impulse response and the autocorrelation function of the input random process, we can find the mean square value of the output random process. Here tau 1 and tau 2 are the dummy variables, the variables of integration. See, here it is function of tau 2 and this is function of tau 1 and tau 2. So here we are integrating with respect to tau 2 and tau 1. So definitely after integration, this will be a constant. So ryy of 0 is a constant. Now we try to find cross correlation between the output and input. See, what is correlation? It indicates the similarity between the two random processes or two random variables. So here we have two random processes, output random process and input random process. The interdependence between the two random processes of the LTI system can be measured by measuring the cross correlation between the output random process y of t and the input random process x of t. So this can be designated as ryx of tau is equivalent with the assumption that output random process and the input random process are while and stationary. Expectation of y of t and x of t plus tau, is it right? Now this can be written as expectation of what is y of t? So minus infinity to plus infinity h of alpha x of t minus alpha d alpha, and we have x of t plus tau. Change the order of integration and expectation, we will get it as minus infinity to plus infinity h of alpha, so expectation of x of t minus alpha x of t plus tau. So we already assumed the input random process is while and stationary. Then this term expectation of this is the Rxx of, it is the function of time lag, is it? What is the time? This is time 1, this is time 2. What is the difference between these two? T plus tau minus t plus alpha. Tau plus. Understood? Here, the time lag t plus tau minus t plus alpha. So tau plus alpha is the time difference or difference between the two times. So can I write this as minus infinity to plus infinity h of minus alpha Rxx of tau minus alpha d of. Is it right? Replace alpha with minus alpha. Then limits become plus infinity to minus infinity. Here you will get minus. Again that can be written as plus minus infinity to plus infinity. Now what this indicates? See, it is in the form of h of alpha Rxx of tau minus alpha d alpha. This integral is the convolution integral except the minus sign here. Can I write this as see, if this minus is not there, what you write? H of tau convolution with Rxx of tau, but minus sign is there. So that's why we are writing it as h of minus tau convolution with Rxx of tau. So therefore, the cross correlation between the output and input random process is Ryx of tau, that equivalent to h of minus tau convolution with Rxx of tau. Is it clear to you? What is Rxy of tau? This can be written as expectation of x of t1, y of t2. Otherwise, you can write it as x of t, y of t plus tau. So this is expectation of x of t. This will become minus infinity to plus infinity h of alpha. See, y of t is equivalent to minus infinity to plus infinity h of alpha x of t minus tau is it? Is it right? So therefore, what is y of t plus tau? Minus infinity to plus infinity h of alpha x of t plus tau minus alpha. So therefore, you write that here x of t plus tau minus alpha. Understood this? This step is important. We already know y of t, simply replace t with t plus tau, we will get y of t plus tau. So therefore, this Rxy of tau is equivalent to, change the order of integration and expectation. We will get minus infinity to plus infinity h of alpha, and this is expectation of x of t and x of minus alpha. So what this indicates, this is the Rxx of, what is the time lag here? This minus this, tau minus which is equivalent to h of tau convolution with Rxx of Is it clear to you? So we obtain the cross correlation between output and input, input and output. See, both are not same. See, Rxy of tau, Ryx of tau, both are not same. But we already know that. See, you can verify that this Rxy of tau equivalent to Ryx of minus tau. That you can verify. Is it? That is satisfied. In the same manner, what about this Ryy of tau? Y of t, y of t plus 2. This can be written as expectation of minus infinity to plus infinity h of alpha x of t minus alpha d alpha y of t plus and this can be written as minus infinity to plus infinity h of alpha expectation of, so let it be x of t minus alpha and y of t plus tau. Then this will become, so this become h of minus alpha, this is Rxy of tau minus alpha d alpha. Is it right? Now this can be written as h of minus tau convolution with Rxy of tau. Then you can write this Ryy of tau is equivalent to h of minus tau convolution with, what is Rxy of tau? H of tau convolution with Rxx of. Therefore, this can be written as h of minus tau, h of tau, or xx of. So this is the relationship between the ACF of the output and the ACF of the input. Understood? The autocorrelation function of the output random process Ryy of tau is equivalent to h of minus tau convolution with h of tau convolution with Rxx of tau. So with these results, now we see the frequency domain characterization of the LTI system. Input is a random process, output will also be a random process. So we see all these relations, how they are related in the frequency domain. So we try to find the power spectral density of the output random process. So we already know that this Ryy of t is equivalent to h of minus tau convolution with h of tau. See, convolution is commutative, so you can write either way, h of tau, h of minus tau, Rxx of tau, Rxx of tau, h of tau, h of minus tau, either way can write. We have three laws of the convolution. Convolution is commutative, associative and distributive. So this is Rxx of tau. So once you know the relation in the time domain, we can obtain the power spectral density of the output random process. So take Fourier transformation. Then you will get SYY of omega is equal into, see, Fourier transform of h of minus tau is h of minus omega. This is h of omega. This is understood this? So this, see, if h of t is real, h of minus omega can be written as h star of omega. That is a conjugate symmetry. So therefore, this is h star of omega, h of omega, so which is equal into mod h of omega whole square. So this is very important relation which relates the power spectral density of the output random process and the power spectral density of the input random process. This is the relationship between the power spectral density of the output is equivalent to mod h of omega whole square multiplied with PST of input. I think you might have studied the same relation in the case of deterministic signals. Have you studied? In the case of deterministic signals also the same relation holds. The relationship between the PST of output and the PST of input is same. Now we try to see the cross spectral densities. So we already know that Rxy of tau is equivalent to h of tau convolution with Rxx of tau. Is it right? This implies the cross spectral density is equivalent to h of omega multiplied with and we have one more relation, Ryx of tau is equivalent to h of minus tau convolution with Rxx of tau. So this implies Syx of omega is equivalent to h of minus omega convolution with, multiplied with. So these two are called the cross power spectral densities of the input and output of the LTS, which is excited by random input, random signal. See, the LTS system can be characterized in the time domain as well as in the frequency domain. In the time domain, we have the convolution, but if you transform these equations into frequency domain, they simply become the multiplication. Alright? So therefore, the analysis of the LTS system is very simple when we transform all the equations into frequency domain.